Good morning. My name is Shihui Qiao, and in my screencast, I am going to introduce you to two-dimensional polymers and provide an overview of various strategies of these important molecular networks. A two-dimensional polymer refers to a network layer with one monomer unit thick, which can form molecular objects of well-defined shape, representing a significant departure from 1D and 3D polymers. The use of 2D polymers is an intriguing and new future approach to materials chemistry for various reasons. Firstly, 2D polymers possess enhanced mechanical properties and stability compared to the entangled 1D polymers. Secondly, high surface bulk ratio of 2D polymers offers a means of organizing chemical functional groups, while even quite subtle changes in chemical structure can dramatically and adversely affect the solid state structure of 1D polymers. Finally, 2D polymers frequently integrate stable pores of defined size and shape, providing high specific surface area suitable for post-synthetic functionalization. Due to the unique physical and chemical properties of 2D polymers, these systems have potential applications in many fields involving conducting materials, membrane, photoelectric and dielectric systems, catalytic and lubricant characteristics. I will now introduce some of the synthetic methods available to access two-dimensional polymers, and I will show you both flux-type approaches and interface-assisted methods. First, let's look at flux-type approaches to 2D polymers. This refers to the direct synthesis of 2D polymers in solution without any interfacial assistance. One method is organic 2D polymers via covalent synthesis. Organic 2D polymers are generated through small repeating units connected by covalent bonds. For example, through a cascade of intramolecular oxidative cyclodehydrogenations, monomer 1 was transformed into the corresponding flat polyaromatic hydrocarbon 2. This method represents an important step towards improved graphite model structures. However, the enormous synthetic complexity and insufficient solubility of these products hamper in-depth structural characterization and also preclude use of the materials as starting materials for further functionalization and growth. Another example of flux-type synthesis is self-assembly by non-covalent supramolecular approaches. Let's look at an example of a single-layer 2D honeycomb supramolecular framework driven by pi-pi stacking interactions. First, 1,3,5-triphenyl benzene compound that bears 3 BP units on the peripheral benzene rings was designed and synthesized. Then, 3 hydrophilic groups were introduced to the central benzene ring to suppress 1D stacking of the triangular backbone and to ensure solubility in water. By mixing the structure with CB8 in water, a monolayer 2D framework was successfully obtained in the liquid phase, driven by pi-pi stacking of 2 independent BP units in the cavity of CB8. Next, I want to focus on interface-assisted approaches to 2D fragments. An interface is capable of directing the assembly of precursors in a confined 2D space, which plays a crucial role in controlling the structure of the final products. Additionally, some interfaces, such as metallic or metal oxide surfaces, not only act as templates but can also catalyze the polymerization of 2D polymers. First, let's look at an example of interface-assisted synthesis of 2D polymers at air-liquid interface. An isoacetate solution of benzene hexacyl was spread onto the surface of an aqueous solution of nickel acetate and sodium bromide. Through coordination reaction between benzene hexacyl and nickel acetate, a monolayer 2D nanosheet was formed at the air-liquid interface. Interface-assisted synthesis of 2D polymers can also be achieved at solid-liquid interface. The positively charged Gemini monomers Ma11-11Ma were initially adsorbed onto a negatively charged substrate through electrostatic interactions. Above its critical micelle concentration, the monomer formed a uniform bilayer covering the solid surface. Then, the bilayer of Gemini monomer was cross-linked using free radical polymerization with a water-soluble initiator. During the polymerization, covalent bonds formed between the methacrylate groups from both upper and lower layers of Ma11 to 11Ma, threading the monomers into 2D networks.